Hello everybody, welcome back to another video. Today we're going to be looking at a very interesting problem as always. As you can see right here, we have e to the x is equal to the natural log of x. Now there's something very unique about this equation, and for today we're going to be solving for a solution of x. But if you haven't noticed already, there's something very peculiar about this. Let me move this to the side. Alright, if we take a look at the graphs of each of these functions, you'll notice something very interesting. In blue here, I'm going to draw e to the x, like that. And in red here, I'll draw ln of x. ln of x looks like that. More like this. Yeah. This is an asymptote for e to the x, meaning it'll infinitely, as x goes to negative infinity, it'll approach y equals 0, this line. And as x goes to 0, the y value will approach negative infinity for a natural log of x. But we're trying to find when e to the x is equal to ln of x. So what does that mean? We're trying to find a value of x that exists on both of these graphs. But if we a value of a point on the graph that satisfies both of these graphs. But immediately right here you can see that there's no intersection. There's no intersection of these two graphs. So how can we find a point where these two are equal? Maybe here? No, you can't draw anything. There's no point you can draw here. So that means the solution to this equation is not going to be real. And we can notate that like this if you're curious. This will not exist in the set of real numbers. But yeah, all right, let's get right into the solution. So now we know that the solution to this equation will be complex, meaning it'll involve I at some point. Now, immediately when you look at these equations, you have to take note. How can we even isolate for x here? There must be a clean way to do it. Well, let's see. Maybe we can get rid of this e by taking ln on both sides. So let's try that. I'll write it in red here. ln and ln. So on the left here, we have ln and e. Those cancel, leaving us with x is equal to ln of x. Now that looks really bad, and I don't think I can solve for x from this form. It looks very messy. Anyways, so maybe we messed up already. Let's go back. So maybe that step was wrong. What's something else we can do? Maybe we can get rid of this ln of x by exponentiating both sides. So what that means is we can take e to the x and then e to the ln of x. So the e and ln of x cancel, and on the left-hand side we have e to the x, which is equal to x. So maybe if we divide both sides by x, we can get somewhere. Let's see. E to the x over x equals 1. Not quite. So maybe let's try this. Maybe we can write this over x as in terms of a negative exponent. So I have x to the negative 1, e to the x equals 1. Well, if you recall our Lambert W function, if we do Lambert W, Lambert W, if you don't remember, is this, by the way. The Lambert W of x times e to the x is equal to x. It's a special function in mathematics, and I can do an in-depth video on it if you guys want later. Very handy for solving some cool functions. So yeah, once again, if you have something times e to the something, the Lambert W returns that something. But right here, if we look at this, we have something, we have something right here, then we have our e, but these two need to match. So is there any way that we can make them match? Not quite, not in a clean way, really. I can't really even see one, to be honest. If I exponentiate both sides, then this e comes here, and this gets convoluted because these are multiplying, and then it doesn't look too nice. So maybe we already messed up as a whole. So let's go back to the beginning. How can we approach this problem? If we have the Lambert W function, as I said, we know that the Lambert W of something times e to the something returns that something. So we just need something here that matches this, and we need an e to this. So I'll call this u, then we need u here, right? So to apply the Lambert W function, on this side, we just need, as I said earlier, we need to have something here that matches. So effectively on the left, I need to add an x here, so I can apply the Lambert W function and get back an x. So that way I can get rid of all that convoluted stuff there. And over here, on the right-hand side, I need to have times e to the something. But what's that something that has to be in the exponent? That something should be the same thing as the coefficient, as the Lambert W suggests right here. So that something should actually be ln of x. Now here's the really cool part. Look at what I'm multiplying by on the left-hand side, x. And what am I multiplying by on the right-hand side? E to the ln of x. But e and ln cancel, so that's equal to x. This entire term is also x. So that means this is a valid multiplication. If you didn't catch that, this is all we're doing. Multiply both sides by x. X times e to the x equals x ln x. And this is just with our standard algebra because we're multiplying both sides by x. And now we can rewrite this as x times e to the x equals, we have ln of x times e to the ln of x. Because remember, these are opposite operands, e and ln. So this is a valid way to write x. All we did is just multiply both sides by x. That's the beauty of it. Now we can take the Lambert W of both sides. And remember, Lambert W of something times e to the something returns that something. So on the left-hand side, we have something times e to the something. That'll return x. And here we have, this will return ln of x. Absolutely beautiful. And it works out perfectly. But how do we solve this now? Maybe there's an easy way to do it. If we look at the graphs, once again, x is like this, and ln of x is like this. Once again, they don't intersect, meaning our solution is complex, which is the conclusion we drew earlier, which is pretty cool. But to solve this equation, let's try exponentiating both sides like this. So now we have e to the x, and e and ln cancel. This means e to the x is equal to x. But are we done yet? How can we solve this equation? Well, once again, we're going to have to use our Lambert W function because we have x as just a number here and then x in the exponent as well. So let's see how we can manipulate this to use the Lambert W function. Let's try dividing both sides by e to the x. So everything over e to the x. On the left-hand side, I have e to the x over e to the x, which is just 1, equals x over e to the x. But what's another way I can write this? I can just write this as x times e to the x all to the negative 1. That's a valid way, because with our negative exponents, this is how it works. So, furthermore, I can keep going and rewrite this. 1 equals x times, and since this is in this special form, exponents multiply as an algebraic property. So we have x times e to the negative x equals 1. But are we ready to use the Lambert W function again? No. The Lambert W function is something times e to the something, specifically. But this is something, I'll do this in blue, something times e to the negative something. So these two are not the same. We can't use the Lambert W yet. So are we stuck? Absolutely not. We can multiply both sides by negative 1. So I'll just switch around the sides. I have negative x times e to the negative x equals negative 1. Now, all I have to do is, since these two somethings are the same, I can apply the Lambert W function here, Lambert W here, and then this will return me negative x equals w of negative 1. And remember, this is the solution of e to the x equals ln x. We just multiplied by x, we got another form of x, we solve for this, and we get negative x equals w of negative 1. Then we multiply both sides by negative 1. And ladies and gentlemen, we get x equals negative w of negative 1. That is absolutely beautiful. This is indeed a complex number, and there's a much, much more in-depth way of solving this. I can do that in a separate video if you'd like. But essentially, this is in the form of a plus bi, and it's irrational, of course, the a and b. And it does indeed satisfy the question of e to the x equals ln of x. It's amazing how the Lambert W function has so many uses, even for finding complex solutions for this. And it's quite astounding, really. And if you really look at it, the Lambert W function, you guys can search this up as well later, it looks sort of like this. It goes on and on and on. But there are you'll see that this fails the vertical line test if you guys learned that, meaning it's not entirely a function. But that's why I drew this in two colors, because the multiple branches of the Lambert W function represent different segments of this function, and each of those individual segments are indeed a function. I forgot what this value is right here, but the Lambert W function is not quite defined for values of -1 whatsoever. So finding W of -1 is quite a challenge too, and that's a separate topic as well. And there are many complex forms of even evaluating that. And then we negate that, and we get our solution. Let me know if you guys enjoyed this video, if you want to see more things like this, and you guys can submit some more math problems on my Google form or even in my comments, and I'll do them for my next videos. Let me know if you have any questions. See you guys. Thank you.